chapter 2 and chapter 4, we spent some time talking about isomers. And in particular, introduced a new kind of isomerism called conformational isomerism. Conformational isomers are defined as isomers that can be interconverted through rotation about carbon-carbon sigma bonds. Now we're going to talk more about stereoisomers, and it's an important enough topic in organic chemistry that it has an entire chapter devoted to, chapter 5. And we need to start by remembering the definition of stereoisomers, which is isomers that have the same connectivity of atoms, but a different 3D arrangement in space. We introduced stereoisomers, we broke that down into subclasses: geometric isomers and optical isomers, which are also referred to as enantiomers, where optical isomers are related as object and non-superimposable mirror image. So they are mirror images, and you can't rotate those mirror images in any way to get them to overlay on top of each other. They're non-superimposable. Whereas geometric isomers, we have cis-trans, and in octahedral complexes we have facial and meridional isomers. And these are not mirror images at all. We don't have octahedral carbon because carbon is only four bonds. So we will not, in fact, be interested in facial and meridional isomers. But we're going to need to be a little bit more specific about some of the types of stereoisomers that don't fit neatly into either of these two classes, either optical isomers or geometric isomers. And we have another term, diastereomers. And stereoisomers that are not related as object of mirror image. So if they're related as object of mirror image, but they're not superimposable, they're enantiomers. And if they're not related as object of mirror image in the first place, obviously then they're not superimposable, then they're diastereomers. Geometric isomers are all, strictly speaking, diastereomers, but we generally reserve the term diastereomer for molecules that have what we call chiral centers. Where a chiral center is an atom, usually carbon, but it could be nitrogen or phosphorus, that is attached to 4 different substituents. if a molecule has one chiral center, it will definitely impart a physical property referred to as chirality. Chirality describes the ability of a molecule to rotate plane polarized light. Two enantiomers, non-superimposable mirror images, will rotate plane polarized light in equal and opposite directions. And they, in fact, have identical physical properties except for the ability to rotate plane polarized light. So the different enantiomers cannot be separated by boiling them apart or by crystallizing them apart or any other physical property. And obviously you can't separate things by using the ability to rotate plane polarized light. So we have some definitions. We have chirality, which is a property of optical isomers, the ability to rotate plane polarized light. We have enantiomers, which are related as object and non-superimposable mirror image, and they will rotate plane polarized light in equal angles in opposite directions. We have diastereomers, which are stereoisomers that are not related as object and mirror image. Generally, we'll use that term for molecules that have a chiral center, which is sometimes referred to as an asymmetric carbon. And an asymmetric carbon or a chiral center is a carbon attached to 4 different substituents. Any carbon attached to 4 different substituents will not be superimposable on its mirror image. And so you'll have a pair of enantiomers. But it's possible to have multiple chiral centers such that you are no longer related as object and mirror image, and that makes a molecule or a pair of molecules diastereomers instead of enantiomers. Enantiomers, diastereomers, geometric isomers, these all refer to relationships between a pair of molecules. Geometric isomers are not related as object and mirror image, so they are diastereomers, but they're also geometric isomers. They don't necessarily have to have chiral centers. It's important when you're thinking about these terms to clearly distinguish between a chiral molecule, which is a molecule that can rotate plane polarized light, and a chiral center, which is an atom, usually carbon, that's attached to 4 different substituents. The chiral center describes the properties of an atom within a molecule. The chirality of the molecule refers to a property of the molecule itself that can be measured. There are 3 systems of nomenclature in stereoisomers that we need to familiarize ourselves with. The first is a D and L, a small d and a small l, often italicized, where D stands for dextrorotatory. And it's also given the plus sign, which refers to a clockwise rotation of plane polarized light. And L stands for levorotatory. It's given a minus sign. It refers to counterclockwise rotation of plane polarized light. D and L refer to properties of molecules. And they can only be determined experimentally by measuring. You can know the three-dimensional structure of a molecule, which you can obtain often by X-ray crystallography, but that won't do anything towards telling you whether the molecule will be dextrorotatory or levorotatory. You have to actually put that solution in the presence of plane polarized light and see what happens. The second is R and S, capital R and capital S, where R stands for rectus and S stands for sinister. And these don't refer to an actual rotation of a plane polarized light, but they are properties of a stereo center or chiral center or asymmetric carbon. Are interchangeable terms, and they are based on a set of substituent priority rules developed by Kahn, Ego, and Kralov. Where R, rectus, refers to clockwise motion from largest to smaller substituent priority. And sinister refers to a counterclockwise motion, larger to smaller substituent priority. The R and S nomenclature is not experimentally based, it's theoretically based. And based directly on known three-dimensional structure. Molecule. And is completely unrelated to DL nomenclature. So it's possible to have a clockwise motion from larger to smaller substituent priority, and thus have an R stereo center, and yet rotate plane polarized light in a counterclockwise direction, and so be a levorotatory compound. The third set of nomenclature is capital D and capital L, and this is based on Fisher projections of glyceraldehyde, which is a 3-carbon sugar, the simplest sugar, 2,3 dihydroxypropanol. So glyceraldehyde in its Fisher projection can look like that, where the OH group is on the right, and that is the D isomer, or it can look like this, where the OH group is on the left, and that is the L isomer. It happens that capital D glyceraldehyde is in fact dextrorotatory, and capital L glyceraldehyde is levorotatory, but that was actually by chance. Fisher took a wild guess and happened to guess correctly when he looked at the 3-dimensional structures and assigned one of them to the dextrorotatory isomer and the other one to the levorotatory isomer. So it's based on glyceraldehyde, and it's based on the chirality of the highest numbered stereocenter. Glyceraldehyde has just one stereocenter, which we often abbreviate with a mark with a little asterisk. So the D and the L is based on whether the highest number stereocenter, in this case at carbon 2, is on the left or on the right in the Fisher projection. So it's particularly useful in sugars and amino acids. So you'll see it used a lot in biochemistry, where sugars and amino acids are important molecules. So we have these 3 different sets of nomenclature that are largely unrelated, although the capital D and capital L is related to the R or S stereocenter at that highest number stereocenter. For molecules that only have one stereocenter, there'll be a direct correspondence. For molecules that have multiple stereocenters, the D and the L refers to just the one stereocenter of that. So we need to talk about in the next couple of videos how we go small D dextrorotatory or small L levorotatory, and we need to talk about what are these conjugate substituent priority rules and how do those apply to determining whether a stereocenter is R rectus or S sinister. And remember that the R and S nomenclature refers to the property of a chiral center, whereas the D and L nomenclature refers to the chirality properties of a molecule. Chiral molecules can be E or L, chiral centers can be R or S. And in the next video, we'll talk about measuring the counterclockwise or clockwise rotation of plane polarized light and how we can use that to define how optically pure